In linear algebra, we talk about things called linear transformations. And a linear transformation is a very, very special type of function if I think algebraically. And the reason I'm bringing that up is because we're going to look at something that's really similar in concept. So if I said f of x, is, let me just make up an arbitrary function, x squared. Is this a linear transformation? Well, a linear transformation has two properties. One is that if I said f of x1 plus x2, that's equal to f of x1 plus f of x2, and f of kx is equal to k f of x. Now, when we're doing them from a matrix and a vector standpoint usually, but this applies across the board really to all functions in all dimensions even. So, is this true? If I said f of x1 plus x2, does that equal x1 squared plus x2 squared?
No.
No.
It does not.
No, because I'd be squaring that, I'd get something else. If f of x equaled cosine x, does f of the sum equal the sum? No. In fact, is there even a function that makes this true? I mean, what if I just said something as simple as a line? Would that work? So would f of x1 plus x2, well, that would be x1 plus x2 plus b. Oh, that's mx1 plus b plus mx2. No, it still doesn't work.
Yeah.
So does it ever work? Yeah. Yeah, it does work. That's it. A line through the origin. Because one of the most important aspects of a linear transformation is if I input the additive identity of whatever I'm working with, I have to output the additive identity. Think of this in multiple dimensions. You're in R3, you're in R4. Oh, so I'm inputting in, 0, 0, or 0, 0, 0, or 0, 0, 0, 0, my output would be the number 0. So it's a linear transformation. It's linear, but it has to pass through the origin, regardless of the dimension. That's a really, really important trait, and I can model that function. Now we're going to talk about something called a homogeneous function. Now, it's nothing to do with that, but it also has some very strict rules of what makes it a homogeneous function. It's a linear transformation, which is a function, if and only if, well, I erased them. Okay, that f of the sum is the sum of the things and scalar multiple and so on. Something is a homogeneous function if and only if, okay, and we're thinking about this again having multiple inputs. We're actually thinking of this to start off like a three-dimensional function. It doesn't have to. I can do it. I'll start with a one-dimensional. F of x equals x cubed. Let's start with something like this. What if I said f of tx? What would that be?
T.
I'll use a t because in the textbooks use a t. I like using k's, but we'll use t's.
T
Won't
cubed
that
x
be
cubed.
t cubed x cubed?
Yes.
Which is t cubed f of x.
Yes.
Huh. I didn't factor out the t, it came out as a t cubed,
Right.
but it still worked. So we would say this function is homogeneous of degree 3. I could have a homogeneous function in a higher dimension. Let's do a homogeneous function of degree 3 in 3 dimensions. So what if I said f of x y equals x cubed plus y cubed? Now what is f of tx comma ty? Do you see it'll be the same thing? It'll be t cubed times this. So if I have a homogeneous function of a particular degree, that means if I replace my variable or variables, we just arbitrarily say t times the variable, the t gets factored out to an exponent. Does that make sense? So like the linear transformation has some very, very strict rules and it hardly ever applies. But when it does, I can recognize it easily.
So you're saying that a homogeneous function is the second condition in linear transformation?
No. It's a similar type of concept.
Okay.
When I define linear transformation, it has these very, very strict rules of how I can manipulate. So f of the sum is the sum of the f's, that kind of thing.
Okay.
And then f of t times something, the t can be literally factored out. In this case, it's only the f of t times something, but the t gets factored out to an exponent.
To
Now,
the same
what-
exponent as the function. I mean, sorry, to the same degree as the function.
Whatever degree this is factored out as tells me the degree of homogeneity, that's the right word. Could that just be to the first power?
Yeah.
Yeah, what if f of x is just x? That's boring. That would be homogeneous of degree 1. But if I said f of x is x plus 5, it's not going to work, is it? F of x is cosine x. It's not going to work. Most things it's not going to work, is it? It's pretty much things that look like exponentials, just really, really strict. So a homogeneous function. Now, I'm not crazy about the use of the word homogeneous here, because these are not homogeneous equations. If they were homogeneous equations, then what would these have to equal? Zero. But we can have a homogeneous function and then find out where it equals 0, and that's just wrong. You know, a homogeneous equation involving a homogeneous function. I'm going to try to avoid that happening, but we're using the same word to mean completely unrelated things. Okay, again, homogeneous equation means my equation is equal to 0, or my system of equations, they're all 0. Okay, that's for a very specific purpose. But the homogeneous function has this. Now, if I have a homogeneous function, or a homogeneous differential equation, that's the next thing we're going to look at, then there's certain things I can do that make my life much easier. So let's suppose I had something of the following form. In fact, I'm going to be lazy and grab one out of the text. xy plus y squared dx plus x squared dy equals 0. This is just a differential equation. Is it separable?
Yeah. Oh no.
What really makes it not?
The sign.
Darn plus sign. Yeah, it's not going to be separable. Is it going to be first order linear?
No.
I got a y to a power.
Yeah.
Is it going to be? Is it going to be exact?
Could be.
I mean,
Maybe.
it could be.
Yeah.
Let's see, if I take the
Weird-
partial with
weird
respect to
integrating factor.
y, I'd get x plus 2y with respect to x, I'd get 2x. Yeah, then
You could make it
maybe,
probably.
maybe I can find an integrating factor. Yeah. But it is homogeneous of degree 2.
Yes.
Without me even testing anything, how can I come to the conclusion that it's homogeneous of degree 2?
X
Because we have
squared,
a
y squared.
Because every term is second degree. So if I replace x or y with tx, ty, I would be able to factor out the t squared from every single term. The fact that every term was the same degree is what makes this homogeneous of degree 2. Using the same ruling we just did. Again, replace your variables with tx and ty. Won't I have a t squared then on both sides? And I could literally get rid of it from the equation. That's not even a thing. But if I have a differential equation that's homogeneous of a particular degree, there is a technique that I can use to solve this one. It's not my favorite technique. It can be challenging. But there's a technique that we can use involving a substitution that will make this separable. This is not separable, but I can make it separable.
So how do you state that the function is
Well,
homogeneous?
the differential equation is homogeneous of degree 2.
Okay, so
Because if I replace all of my variables with t times that variable, then I'm going to have a t squared in every single term, and I can factor that out of the problem. That's an identification thing. I'm not going to use that, by the way. I'm never going to introduce the t and then take it out of the problem. That's an observation. If any one of these was third degree, it's a completely different problem. Doesn't mean I can't do it. I just can't do it using this technique. So what we're going to do, now, by the way, bless you, it doesn't matter if I wrote it in this form or if I had dy dx and then the other term. It wouldn't make any difference. So what we're going to do is we're going to say, let y equal u times x. By the way, I could just as easily say, let x equal u times y. And sometimes I'll say, let's use v this time just for fun. It doesn't matter. Most of the time when we're going through this course, we'll use either u or v as our extra function. It doesn't matter. It's not going to change anything.
Is letting y equal ux the same thing as how we're letting the y over there equal tx?
No, because this t technically we could think of as a coefficient. We're going to think of this u as actually being a function.
Okay.
And by the way, we're going to run into this many times throughout this course. This feels like cheating. I'm saying there exists a function u that makes this true. In every conceivable problem you can think of, Just, I want to make this sure this is really obvious. What if y is the function, I don't know, e to the x? Just, make up a function for y. I'm absolutely guaranteeing you that y is equal to u times x. Because all that has to happen is that has to equal e to the x, therefore u would be e to the x over x. I can do this for every problem that exists. This is like trivial. This is true no matter what y is. Why? Because all that I have to have happen is y divided by x just has to be u. Does everybody understand that it doesn't matter what y is, y divided by x, that's what I'm going to call my u. I don't know what u is. And that sounds terrible, doesn't it? U R, U B. I don't know what u be. It just sounds like really bad English, doesn't it? We're not necessarily interested in finding what u is specifically as we are solving the differential equation. It may turn out that we can find u, but mostly I want to find the y in that case. So I start with this, therefore, and here's the key step of the problem. And by the way, I want to applaud you guys. On the first quiz, I gave you a problem and asked if something was a solution. And the problem I think involved like t e to the t, which meant when you did the derivative, you had to use product rule. Every class before you, believe it or not, the majority of people on that first quiz totally tanked that one. They literally forgot there was such a thing as the product rule. But almost everybody here did that. They executed that one very, very well. I could care less what the answer was, because I can easily tweak the problem and make it so it doesn't work. But you all did the product rule. Then you found your second derivatives. You substituted them incorrectly. I was happy with that. I was impressed. I didn't have to tell you, hey guys, be aware, But strangely enough, most classes, they don't get that one right off the bat. They go, oh yeah, there's that product rule thing. I forgot about that. There's a product rule. U is a function of x. U is not a coefficient. We're going to do stuff like this all the way throughout the semester. But we won't necessarily write u of x. It's implied. Well, what do you mean? Why won't we write u of x? Well, do we write y of x?
No.
Not usually. But if u is supposed to be a scalar, we'll indicate that, and we'll probably use like literally a k or a c. We kind of reserve those. When you see u's and v's used, like you did, right, integration by parts. When you see u's and v's, we usually think we're probably using that notation because it's a function of x. It's not like it's an absolute requirement. It's just that's what traditional is. So first times derivative of second plus the second times the derivative of the first. Okay. Things I'm using this notation. So if I change this to the different, this is actually called differential notation when you break it up. Tell me. What do you think? That kind of has an integration by parts feel to it, doesn't it? Would that work? Because now if I said let's do everything, dx. Again, if I integrated everything with respect to x, that's exactly what if I did this dx, that's the same as this. If I did this dx. So why do I need this notation? Because I'm going to substitute it into this equation right here.
Didn't you say it was problematic to be multiplying by the differentials?
You're not multiplying it. These are instructions. I have to integrate ultimately with, let's suppose we could carry that one on. I'm going to have an integral with respect to x and another integral with respect to y. But based on this substitution, I'm now going to have an integral with respect to u and an integral with respect to y ultimately. That's what we're doing. We're creating a new problem with this substitution. So in other words, it's the integral of dy is the integral of u dx is the integral of x du, or plus the integral. So when I do the substitution, what will I get?
Ux.
I'll get x times ux plus ux, plus ux quantity squared dx plus x squared,
Times u.
all of that. So how about x squared u dx plus x cubed du? Again, du and dx and dy are instructions that I'm going to integrate with respect to that variable, but we've changed the problem. There's no longer a y in the problem. If I did this right, let's see. Make sure I wrote the problem down correctly. I don't want to, I wrote the, okay, good. Last thing I want to do is, oh shoot, it should have been this. Now, can we put things together? We're gonna have a, move the u to the other side in a bit. So what do I got here?
UX.
Decide what order you're gonna write. If we write u times x, then later don't have x times u. That gets confusing. So how about ux squared plus u squared x squared plus ux squared? Everybody cool with that? Equals
Negative x cubed d.
what was the promise I made before I started this particular problem? I said if it's homogeneous of a particular degree and we make a certain substitution, we will create what kind of problem? Separable.
Differential.
Well, let's clean up the left side. Can anything combine? I think these guys can.
Yeah.
So this is now 2ux squared plus u squared x squared. Huh. Wouldn't that just be 2u plus u squared all times x squared?
Yeah.
Can I manipulate this? Can I move things around?
Mm-hmm.
Yeah, but which way do I want to go? I want all the x's on the left. I want all the u's on the right. I'll move over here. If I'm doing this problem correctly, the algebra of what I'm doing right here usually it's not very taxing. It's just never going to be real complicated. You're not going to see a lot of transcendental functions. That's a joke. Okay. You're not going to see any. Why? Because there won't be homogeneous functions. So you're only going to see exponents, polynomial-ish things. Can I see square roots?
No.
What if I had a square root of x squared plus y squared? Then technically that would be homogeneous of degree 1. Think about what happens to the t at the end. I can have square roots. That's not a problem. Can I have quotients? Ooh, that one's a little bit trickier because I can't have a negative degree, but I don't know, depending on the way the quotient looks. I'm not saying what you can't have, but mostly it looks like this. So I'm going to move this guy that way, and I'm going to move this guy that way in the denominator. So what will that leave me with? I think I'm going to get negative 1 over x dx on the left, and I'm going to get 1 over 2u plus u squared du on the right. Does that look about right to you?
Yeah.
Again, if I made a mistake, please, let's figure it out.
Is that x cubed on the right side or x squared?
That's that x cubed right there. But I also had an x squared right here, so when I brought that over, so that's why we use this notation, because then segues very nicely into this. I'm pretty good on the left side. I'll let you guys do the right side. You should have come to my Calc 2 class today. Do you know what we did the whole second half? Partial fractions decomposition. This is u times 2 plus u, or u plus 2. That's not a complicated one, but I'll walk through it because this actually is a technique we will use in this class. Strangely enough, though, we won't use it as much on integrals as we will on other things, but it does come up on occasion. Okay? So, off to the side. I've got 1 over u times u plus 2. I'm going to walk you through because I know it's been a while. Does that look familiar?
Yep.
You're going to break it up. Now, I remind people, when I put everything over a common denominator, I'm going to do that. A, u plus 2, plus b, u, all over this. Now I'm going to equate numerators, which means the next thing I have is 1 equals a times u plus 2 plus b u. But if I know I'm going in that direction, I'd rather just go directly there. A lot of folks say, wait a minute, how do you do that? You can't just multiply through by the denominator because it might be 0. No, actually, we're saying this equals this and we're equating numerators. But since I know that's where I'm going, I can go directly to that step. Now, there's 2 ways I can do this. One is I can gather the terms, if you remember. So I'd have a plus b times u, and then what? Plus 2a.
Equals 1.
Or I can just pick values of u. That's the easier way to do it. So if u equals 0, then the left side is 1 and the right side is what?
2a.
2a?
Yeah.
which tells me my A is a half. And if U equals -2, then the left side is 1 and the right side is
Negative 2b.
-2b, which means that b is -1/2. That's by far the easiest and fastest way. So that means if I factor out the 1/2, then the second integral is going to be 1/2 the integral of A was,
1/2.
so it was A over U, so it's 1 over U, because I factored out the 1/2. The other one was minus, so minus 1 over U plus 2. Everybody cool with that? By pulling out the 1/2, one of the things I remind even the Calc 2 students, when you leave ugly coefficients in the middle of a problem, our eyes are drawn to the ugly coefficient, not to the function. And we start looking at the coefficient going, gee, what do I do next? It's a coefficient. It has nothing to do with the process, it's just part of the answer. So I usually like pulling it out so I don't get confused with its role. Yeah, Patrick?
The arrows, we could do
That means implies.
Okay.
That only has one only one mathematical meaning in this context, and that implies. How many are in discrete or have had discrete? Yeah, when you're using certain types of symbolic notation in a discrete class where you're using the P's and the Q's and the ands and the ors, you'll use a single arrow, which is really confusing because they mean the same thing, but it's different notation. In a calculus sense, single arrow only has one meaning. It's only used in one context in the history of calculus and beyond. It means it's used in a limit. So I always remind people, if you're using an arrow, I have someone in my Calc 2 class who does this. Do you know what that says? It says 3 plus 4 is not equal to 7. It says it gets really, really close, but never reaches. Arrow means approaches, never reaches. Never use an arrow as an equal sign. Arrow is not equal. It actually is impossible. Yeah, but people will do that. No, use an equal. That's an implication symbol. If A then B means A implies B. That's a logical connective. I'm lazy. It saves me from saying words. Thus, the solution of A is, can we integrate all of these easily?
Yes. Negative.
By the way, I put the negative there. Would it have mattered which side the negative went on ultimately?
No.
No, because it won't affect my final answer. I had to put the negative somewhere. So I have negative log absolute value of x equals 1/2.
Natural log of u over u plus 3.
First one, and then the second, I'll do one at a time, minus half natural log u plus 2. Oops. And there is a plus c. I cannot ignore the plus c because the plus c is going to show up differently. It'll probably show up in an exponent or something goofy. So far, so good?
Well, you showed you showed the absolute values in this case
Because both variables can be negative without any problems. Yeah, without the absolute values, then I just cut my domain in half. So yeah, I do want the absolute values.
Since that 1/2 was outside the integral, should the c also be 1/2? Or does it not matter because it's gonna
It's only after the fact. Now, how about if I do this? Is this c going to change throughout the problem?
No.
I think so.
Probably a couple of times. Because remember, we're going to exponentiate at some point. One thing I can do right off the bat is I can get everything on the same side. I do want to exponentiate at some point. Do you agree? Do you like that answer? I would, by the way, I would really love to write y equals. I think I'm really far from that right now, but I am completely done with the calculus. So if I throw everything, it doesn't really matter which side I throw it on. So if I throw everything over, that's going to be minus. So I'm going to have what? I'm going to have 1/2 log u plus 2 minus 1/2 log u minus just the log of x equals c1. I cannot exponentiate until I have a single logarithmic term, and I can't do that because I have coefficients and plus or minus signs, but that's the easy part. Now, you can bring these up and make them all square roots. Is there something lazier that I could do?
Combine your.
Well, I'm going to combine them all at some point.
Multiply by 2.
Oh, yeah.
How about multiply through by 2? It's like, yeah, I'd rather multiply through by 2. I don't want to have any roots. So if I multiply through by 2, then it says what? Log u plus 2 minus log u minus log x,
Square.
and that guy's going to go up here. The sum of the logs is the log of the
Product.
product, the difference of logs is the log of the quotient. The log of the sum isn't anything, which sometimes confuses us. Yeah.
Oh, why do we multiply by 2?
Because then otherwise I have exponents of a half
Just
all
make
over the
it look
place.
nice.
No, make it more convenient to use because remember the coefficients go up as exponents.
Okay.
So you're going to have fractional exponents all throughout, which is not wrong, but there's no advantage to having fractional exponents. And I might as well get rid of them. So now what is this all equal to?
C2.
C2, good.
So if it was 1/3, we multiply through by 3.
In this context, I would, because I'd rather deal with an exponent of 3 than an exponent of 1/3 in certain cases. It just, again, eventually we're not going to have any log terms. Yeah, so now, can I put this together? Now can I put this together as one log?
Yes.
Log of u plus 2 over ux. Huh.
Would it be x squared on the bottom?
Did I? Oh, thank you. Sorry. X squared. We're almost done. I probably will go ahead and exponentiate now. I think it'll be easier to do that and then substitute. So therefore, can you tell me u plus 2 over ux squared?
C.
I think we're on our last C. By the way, if I thought there was one more, I'd just call it C3. Do you see what the benefit of just renaming your C's rather than trying to keep track? I'm almost done. Why am I not done yet?
Because you have to go back from U to Y.
Yeah, I've got to go back because the original question didn't have any U's in it. So what is U equal to?
Y over X.
Y over X.
Yeah.
So everywhere you see a U, let's write a Y over X. Y over X plus 2, Y over X times X squared. What do you think? Bottom's fine, it's the top that's the problem. So what should I do?
Multiply by bottom. Yeah.
This problem did not have an initial condition. If it did, this is a tricky thing. Where do I find it? I don't know. It's a matter of convenience. But what do I have now as a numerator?
X plus 2, Y plus 2X.
Y plus 2x, doesn't matter what order I write it?
No.
Nah, most of you would probably rather write it like that. And my denominator is?
Y X squared.
So x squared y, and this whole thing is equal to?
C.
C. Can you isolate the y? Ooh. Well, you said first thing I do is multiply
Yes,
both by
yes.
x squared y, then I gather the y terms. Is it mathematically possible to isolate the y?
Yeah.
Actually, it is.
But I don't want to.
Yeah.
Do you want to?
No.
Okay. Can you? Yes,
Yeah.
it's actually not hard. Multiply through, gather the y terms, factor out.
Yeah.
Oh, let's do it just to see what it looks like.
You can split it into two fractions.
Say again?
You can split it into two fractions as well. The y's could go away.
Yes, I can. In fact,
That's a good one.
it might be easier.
Yeah.
You guys know I love doing that. So if I do that, what does the first term become?
2 over xy.
2 over xy, and then the second term is
1 over x plus 1 over xy.
1 over x squared, that all equals to c. Send that guy packing, then take the reciprocal of both sides, and then multiply by the show. By the way, it's icky, but it's arithmetic. It's not. I can write it as y equals. Depending on the nature of things, I probably should because that's kind of the way I set up the problem. My point being, we could not solve the first problem, could we? But by making that simple substitution, we created a separable differential equation that we could at least state as a separable. Whether it's easy to solve or not, we have no control over. This turned out not to be difficult to solve. We did have to use one integration technique, right? We did have to use a partial fractions. On the quiz you just turned in on that bonus problem, did you have to use any integration techniques?
Integration by parts.
Yeah, you did one low-level integration by parts, but you still had to do something. So they come up occasionally. It's not a dominant theme. But there's a reason you learned them way back when is because you got to have a way of answering questions when they do come up. And when they come up, they're probably not going to be killer. So how do you recognize homogeneous? Literally every term is the same degree. Now, xy is a term, right? Y squared is a term. So if I see even one term that's a different degree, then I can't do this. Is this my first choice necessarily? What if? What if this ultimately ended up being separable? Then I should go for separable, because the whole point of this was to make it separable. Separable is still always going to be your first choice if it's there. You can't control it. You recognize separable. In fact, that's the one you should recognize first, because you can get the x's together and you can get the y's together and separate them. There are no sums. Separable's first. What was second?
First order linear.
First order linear, find the integrating factor. And then third?
Exact.
Exact. There is a reason we're learning them in this order. This really is the hierarchy. And if it's exact, it's probably not one of the first two. In fact, if it's exact, it could be this. Do you think it would be very hard for me to design an exact problem that's homogeneous? No, it's actually pretty easy. That would be really, really simple. And let's do that. In case you're wondering, how are the problems in a book created in the first place?
They work backwards.
Backwards.
They're reverse engineered. So I'm gonna go really simple. Let's say I'm thinking I want to keep this really, really simple. Let's say okay. Let's now think, in a sense, think calc 3. There's my potential function. So now I want the force vector, which is the gradient of this, except I don't want to write it in vector form. So take the partial with respect to x, and what is it? 3x squared y squared, and I'm going to write that dx. Now take the partial with respect to y.
2y x squared.
Great. Is this going to be exact?
I have a quick question. How come it equals 0? Like, if we just take the derivative there, shouldn't it just be equal to f?
Well, no, we're solving the differential equation that is equal to 0, because ultimately, what were we going to do? Remember, ultimately, it was really a two-dimensional problem.
Oh yeah, we're slicing it.
In other words,
Yeah.
remember, ultimately, it had to equal a constant because we needed to make it two-dimensional.
Yeah.
Here's where the cheat comes. You asked, where do problems come from? I'm writing your exam. This is where the problem comes from. I'm thinking of a simple potential function. I create this exact equation. Piece of cake. Oh my God, that's so easy. Now, when I take the partial of this with respect to y, it's 6x squared y. When I take the partial of this with respect to x, it's 6x squared y. Now I can solve it. So that's the first layer that I do for an exam. What's layer 2?
I see why it's equal to 0 is because if you take the derivative of c, it's just...
Technically, yes. Now, what did I just do from here to here?
Factor out a y.
I took out a y. Is this exact anymore?
No.
No. Can I make it exact with an integrating factor?
Yes.
You're never going to figure out the integrating factor, will you? Or will it just be y, do you think? Yeah, it'll be y. Now, everybody understand, this is how all problems are designed. We reverse engineer, so I know it's going to work. Now, I just put this problem in front of you. But I put this in front of you today, not last day. Are these both homogeneous of degree 3?
Yes.
Are these both homogeneous of degree 4?
Yes.
So could I use that technique on this problem? Absolutely I could. So my point was, can I have an exact equation that also falls in? Yeah, that was pretty easy. And the reason it was easy is because my potential function was a product, not a sum. Oh, if I made this plus something else, then it would be a lot harder, unless my plus something else was plus, I don't know, x to the fifth. See where this is going? Is it hard to design a problem that fits into a certain mold? No. And it's not all that hard to design a problem that fits into multiple modes. So you're taking the exam and either one of these questions was in front of you. Does it matter how you solve it if you get the right answer? No, but you're not going to have a ton of routes. You definitely have at least 2. You just saw exact or homogeneous function. And so which one should you choose?
Exact.
Oh, exact.
Well, in general, which one should you choose?
Oh,
The easier
so
one.
easy.
Whichever one
Takes less
you
time.
see first. Because easy is relative. If I only see one method, that's the only one I can do. But what if you see exact and you see homogeneous? Your solutions are going to look miles apart, but your final answers should be the same. That's one of the really cool things is there may be multiple ways to do the same problem. There will be occasionally a problem, not very often. Maybe it's also first order linear ultimately. But it's whatever you see first. So based on today's lecture, when you're looking at that, you go, everything's third degree, I'm going to go ahead and go homogeneous. And you're absolutely correct. In fact, on the first one, you'd want to go exact because that would be pretty fast. But on the second one, because you have to find the integrating factor for exact, that's probably not fast, is it? This one's probably a bit longer. So if given the choice, I would probably go with the homogeneous function on this one, because I first would have to find the integrating factor, create an exact problem, and then solve that problem. That's probably as long as anything you're going to do. Okay? But ultimately, we're making a substitution. That's the whole point of today's lecture. Solving problems that we had to make a substitution, which means at some point you may have to substitute back.
And we would always be given that y equals some function
No,
of x.
you are starting the problem.
Oh, so we make the...
You do this. But it's always going to look the same. This part right here is always going to look exactly the same for this problem. Depending on the nature of the problem, I've never really seen a good argument, but sometimes I'll see authors do the same problem, but they'll say because of the nature of the problem, it might have been easier to go let x equal vy and then go that route. Does it really matter in the long run? Probably not. But what if the nature of this problem, you notice everything was in the denominator. Wouldn't it have been easier if nothing was in the denominator?
Yeah.
Well, you can't have any control over that. Actually, if I'd done x equal vy, that's probably what it would have looked like. We could still do this problem, but you didn't like doing the parts. By the way, in my final answer, where's my final answer?
Underneath the orange paper?
No, okay, I erased it. In my final answer, do you see any e's or logs? No. So if I had gone let x equal vy, the route would have looked very different, and I still would have got the same final answer.
But what do we do about the absolute values?
Well, in this case, you have to have it because of the log term, but then it comes down, this is something we're going to discuss later on.
Okay.
Remember in the very first question, or the very first quiz, it said something about interval of solution. Would this solution be valid for all real numbers? No, it wouldn't be. And the reason is because there are values where both of these are 0, and that's usually where the line in the sand is, which means the interval of solution here is either going to be only for positive x's or only for negative x's. We don't know that yet. That's something we're going to learn as we go. This would probably not be valid for all real numbers. That's strange, but because there are values that make every term 0, that's usually where the line in the sand is. Well, why would that be a line in the sand? I don't know, because at some point you get a 1 over x. Oh! And if it's not all real numbers, it's whatever interval. There is no problem where you could say it's valid for all positives and all negatives, but not at 0. Nope. It can only be one interval in an answer. That's one thing that's across, I don't want to use the word absolute because it sounds like absolute value. But we do absolute value for the log part so that I don't lose any of my domain. But when it comes right down to it, I can't be on both sides of 0 without having 0 itself. I can be on one side of 0 or the other side of 0. You with me on that?
Leibniz, he always said that these things are continuous functions.
Which things are continuous?
Like integrals and derivatives must be continuous, so like
Yeah,
Over a domain.
Yeah.
So
right. It has to be a continuous stretch of numbers, and I lose continuity at 0. Therefore, I am one side or the other. But the absolute value says it doesn't matter which side. That's another way of interpreting the absolute value. But when it comes right down to it, you're looking at this going, yeah, I can't be all real numbers because I'd get in trouble here. Okay, so that's not a thing to worry about. But it is the right question to ask, saying what happened to the absolute value. I needed it for the purposes of integration, that's for sure. If I drop the absolute value, what if I'm only dealing with negative values of x? Then this does not present a problem. But then again, neither does this because the u also took that into account. Now, think of it as both of them be negative and they cancel in a sense. Okay, now, that is a cool problem, but it is not the coolest problem. We're going to do the coolest problem next.
Can you repeat how we can impose that y equals u of u times x? Like you just...
How can, well, that would be true no matter what because I'm just saying u is going to equal y divided by x. There is a y out there. There's an infinite number of functions out there. Mm-hmm. And if I take that function and divide it by x, now that's my u.
So since we're given this differential equation, you made y equal u times x.
I chose that as my substitution. This is going to be a very common substitution throughout the course that we're going to do, because we'll have a problem that on the surface we can't do anything with it. So we're going to do valid mathematics to change it to a different problem. I mean, when you did a U sub, in Calc 3 when you did a Jacobian, you did a valid substitution to completely change the problem, but allowed you to navigate to the end. We just don't realize how many different really cool tricks there are that allow us to navigate. This is just one of them, but it only applies to this. It only applies to this problem. It has to be a homogeneous function.
So I guess the real question is, how do you determine what other types of substitutions you can do? Like what other tricks? Or how
Well,
do you determine
the
which
substitution, if it's not that one, this is not going to term separable. And by the way, this is the substitution we always do because we don't know what, we know there exists a U. We don't know what U is. So therefore we don't know what Y is. So I just said, let's call U Y over X, and then we're finding out what Y is, which by the way means in the end of the problem, then U was just Y over X. It sounds like we're using circular reasoning. No, make up any function you want for Y. Then if I divide that by X, then that's my U, period. That will work for every function that exists. It's kind of beautiful. Now the next one is something that looks a lot like first order linear. Let me grab the general form, hold on. Oops. Where's my general form? I have it that I highlighted. Oh, here we go. What if? What do we do with this guy?
It's
Ooh, that's
first
the,
order nonlinear.
That's first order linear, okay? We love this problem. It may be our absolute favorite problem, okay?
I like the exact one. It's like a flow search.
Ooh, whoa.
Whoa.
Hello.
This is like
By the way, assume n is not 0.
non-linear, right?
Well, it's definitely nonlinear.
Linear, 'cause you got-
It's definitely nonlinear. But what if through the appropriate substitution, I could make this first order linear? That's crazy.
Parameterized and
No, not parameterize it. It's actually simpler than that. What if, I don't think I showed you this in the text, but oh, the author just states it. I don't think he shows you how to solve it, which is too bad. There is a very, very simple substitution. Now, this is what is called a Bernoulli equation. And I find this utterly fascinating. 2 L's, I think.
Yeah.
Yeah, 2 L's. The reason I find this fascinating, because I've taught math for a long time. Bernoulli shows up a lot in statistics. It's really important. There's other areas of math that Bernoulli shows up. There are 3 different
One,
Bernoullis,
yeah.
and they're all in the same family. They were all alive at the same time. There were 3 different geniuses. Now, I think, I'm not positive because every time I read something it feels like it's different. I think it was like brother, cousin. They weren't all brothers, they weren't all cousins.
Then
We could look it up. I've looked it up and it seems to change every time. But I'm always wondering what Thanksgiving dinner was like when the Bernoullis were together. You have 3 of the all-time greatest geniuses in the same family with the same name, and everything's always called a Bernoulli equation. But every time you hear of a Bernoulli something, it's probably a different Bernoulli. Isn't that crazy? But this is called a Bernoulli differential equation. And because I guess one of the Bernoullis figured out how to do this. You know, probably it was a bet or something. You know, brother said, I bet you can't solve this one. You go, oh yeah, I'm trying to. All right, what if we did this? Let u equal y to the 1 minus n. Assume n is not 0. Assume there actually is a y there. It could be y cubed. It could be y to the -4th. It doesn't matter. It's not y to the 0 because that, or y to the 0 is just first order linear. With this very specific substitution, I didn't figure this out. Bernoulli figured this out. With this very specific substitution, when I follow this through to the bitter end, we're going to get a new differential equation that is first order linear. That's the beauty. That's why this is probably my favorite one, because it's so genius. So, if I follow this through, then what is du dx?
let's just say like
U and y are both functions of x, assume.
Oh, okay.
So this would be what?
1 minus n times y to the
Negative.
oh to the negative n
To just the negative n
times dy
times dy dx.
oh
Okay? Now, it is okay to multiply and divide by variables because one of the most absolute rules, and I always remind people even lower level algebra, we know this, you can never multiply or divide by anything that can potentially be 0. So if we're multiplying, dividing by that variable, that means that variable at no time can be 0. So therefore you really don't have a problem. So if we're saying this variable is identically 0, there's no equation here. But we're just saying the interval that we're solving, we're probably not including 0. So it's usually not an all real numbers kind of situation. Not a problem. So what do you think I should do next? We're going to multiply everything by that quantity right there. Because then that will make the first term du dx. That make sense? So let me write it out. So we're going to do 1 minus n, y to the negative n. I'll put it here. 1 minus n, y to the negative n. And then finally at the end, 1 minus n. Oh, I'm going to write the other terms in. I want this to be really obvious. Of course, the other terms have to be in blue. We know that. So dy dx plus, and this would be p of x y equals, and then this would be y to the, oops, sorry. Ran out of space. Sorry about that. And then this would be
Oh my God.
f of x, y to the n, and
It's coming
then,
together.
what's that?
It's coming together.
Okay. Well, here's why we did this. Because this becomes du dx, which is the first term in a first order linear u equation as opposed to y. But let's follow along. What does everything else become? What does this become? 1 minus n
P
y to the
1 minus
1 minus n. That sounds familiar. P of x. What does this become?
f of x times
How about 1 minus n
times f of x.
times f of x? Someone said it's all coming together quite nicely. This is what I have right now. And everything is still x and y. And everything is still true. I haven't said anything that's not true. So here's what we want to do. Based on this substitution, I want a new I want a new first order differential equation. I don't know if it's linear or not, but that is u and x. So based on this substitution, isn't this quantity, is that du dx right there? Everybody follow that? Followed by what?
1 minus n times u.
1 minus n is a scalar, equals, oh, if I didn't know better, I'd say that's first order linear in u. Now you gotta admit, that is cool. Now, can we solve this?
Yes.
We can certainly set it up. Doesn't it completely depend on the nature of the integral?
Right.
Could the integral be beyond this? Sure. Has it been so far?
No.
Probably not. We can probably navigate, and I even showed you what to do when you couldn't finish the integration. But we can definitely attack this problem to the bitter end. We will in a moment. Now, I get all the way to the end of the problem, and I've solved, and I have u equals the answer. What do you think we should do at that point?
Place it with y.
Let's go back to here and replace u with 1. That's the easiest part of the problem, but I have to do that at the end. We good?
So this is like a pseudo integration factor type thing, but then it's
Well,
actually
no, it
just-
is an integrating factor, but of a new problem. We're going to make this substitution to create a problem that's comfortable. Most of you, I don't want to say you love first order linear, but most of you are very comfortable with them because most of them just weren't that terrible. Okay? And you certainly knew how to set it up, and if nothing else, they were pretty darn easy to recognize, weren't they? That's why it was easy to recognize when you had first order linear, but this one is not because of that additional y term, but based on this substitution, it is. So let me grab one. Let's see. Sorry. Oh, here we go. Here we go. Okay, x dy dx. My eyes are just not working properly right now. 1 plus xy equals xy squared. There we go. I'm truly not interested in the final answer. What I'm interested in doing is setting up a problem that I can navigate, setting a problem at the very least where I can figure out what the integrating factor is. Depending on the nature of the integrating factor, I don't know if I'm going to be able to finish the problem easily or not. You had a bonus problem. Most of you told me you used integration by parts. I'm kind of hoping 100% of you will tell me you used integration by parts. Because if you could do it without, I'm not sure we did it right. But what if you just were totally stumped? Could you have still set up the problem to generate a correct answer? You know, I showed you guys what to do. If you couldn't integrate, you could at least tell me the answer is something times an integral. We can always get to that point in every problem. That's not the question. If I can integrate it, I want to get to the bitter end, but I at least want to be able to set up that thing in case I can't integrate it. So this doesn't look like anything yet, and it's just automatically thrown in this way just to deceive you. You see, this is redundant, isn't it?
Yeah. Divided.
I didn't need to have that there. I could have already hit it. But the idea is for you to look at it and go, let's see, it's homogeneous of a degree, nope. It's it's separable, nope. Right, it's exact, nope. Boy, it doesn't look like first order linear yet. So what I would do on a problem like this, just because of the way it's set up, I'd probably get rid of that in the very first step of the problem. It's not first order linear, but it's Bernoulli. Agreed?
Yeah.
I know I could at least get it to the point where I can find the integrating factor. I know that. Depending on the complexity of the integrating factor, it might be a hard problem.
It's Bernoulli because there's a exponent in the y term, yeah, right?
Because there's a y term period.
Okay.
Yeah, there's my p of xy. What if that were just a y?
It'd
That
still
would
be
be
Bernoulli.
one, so we Bernoulli.
Could I perhaps combine it with this one?
Yeah.
Would that be possible?
Yeah.
Yeah, it would be. So in that sense, would it necessarily technically be Bernoulli? That's kind of a trick question. If that was just y to the first power,
Oh, give you y to
then
the
my
third.
substitution would have been let u equal
1.
1. That's not a substitution, is it?
No.
So if it were a y to the first power, it really isn't Bernoulli. I could have just everybody follow that? If that's a y to the 1, then I just throw it over here. Now I have 1 plus x over x minus 1 times y. And I'd have a 0 on the right, which we're not used to seeing, but does that present a problem actually? No, it makes my final answer easier actually. So I said, we're going to assume there's always a y there, but it's probably not going to be a y to the first power because I could have combined it with the other y. So does it have to be a positive integer power?
No.
No, it could be a negative integer, it could be a fractional exponent. That doesn't actually make it more difficult. It truly doesn't. The fractional exponent only changes the n. It doesn't make the rest of the problem harder though.
I just noticed something interesting here. So when we do this u sub, like usually with u subs, we have our u equals something, and then we just say du equals something, and then dy or whatever. But
Well,
here we have
because of the
dx.
form, sometimes we do the du and the dy, you're right. We did that on the other ones because it's what's called differential notation. We don't on this one because the form of the first order linear, we like to have the derivative term, the whole derivative term sitting there. So that's why I did it in the formal derivative notation. So then it looks like the derivative term because I have it sitting right there. Would it be wrong to have the dx and dy notation? No, but it would look different and I might not recognize it. And that's the problem. If it looks different, I might see it as something else. But if it's in this form, very unlikely we're going to confuse it with something else. So, what is my substitution?
U equals y to the negative 1.
To the negative 1. Then du dx, negative y to the negative 2 dy dx. And actually, go ahead and use the negative exponent. That doesn't cause a problem. Might make it easier, in fact. So, what am I going to multiply everything by?
Negative y to the negative 2.
And it's this equation, by the way, not the original one, because I don't want that x there. It's in the way. So when I multiply through, it's going to be negative y squared dy dx This is the easy part, you're just multiplying. So now it would be plus 1 plus x over x, y, and I'm gonna write it as y to the negative first. And the reason is because that's the way my substitute, see, it'd be just easier for me to recognize. It would be correct to write 1 over y. But then it would look different, and then again, if things look different, I might not see them for what they are. And the whole thing is equal to
-1.
just -1.
I think the first one's supposed to be negative y to the negative 2, right?
What did, oh, thank you, yes. Negative y to the negative 2. Does that look right?
Yes.
Negative y to the negative 2 plus stuff times y to the negative 1. Okay. Now when I do my substitution, this becomes du dx plus 1 plus x over x u equals -1. Okay? For this one, I probably want to pull those apart, don't I? So that's 1 over x plus 1. So my integrating factor is e to the integral of 1 over x plus 1 dx, which is e to the
Natural.
log x plus x, but rules of exponents, right? So this is e to the log x times e to the x, which is just x e to the x. Didn't say I love it, but that's what it is.
I mean, that's awesome.
Not my favorite. That one I don't mind. What do I have to ultimately do you think I'm gonna have to do?
Integration.
Parts. It's only bad if that was an exponent.
Yeah.
Then it's icky. But this is a one-step integration by parts. Okay, everybody cool so far? So let's, I'm gonna erase that. I don't need, that's the formal setup. This feels very Calc 2-ish, in that Calc 2 you learned a whole bunch of methods of integration real close together, and it was all about recognizing which form it is. Well, this is really the same thing. What form is the differential equation?
I'm confused on how you replace the y with the y to the negative first power.
How I replaced, I'm sorry, I didn't replace anything. I said, based on this substitution, this is a true statement mathematically. Now we're gonna multiply both sides of the equation by that quantity. I didn't replace, I just said multiply through by that. Now when I did that,
Oh, okay, yeah.
when I did that, it gave me this. So I had y to the negative 2 times that y. That's where the y to the negative 1. Y to the negative 2 times that guy gave me just 1. Or
Okay.
second guy. Right? I didn't do anything. I just multiplied through. Now, my new equation is first order linear in u. We have the integrating factor. So let's multiply both sides of this equation by x e to the x. Sorry, it's too far. 1 over x plus 1. Now, when I do x e to the x, that makes this a little bit nicer, doesn't it?
Yeah.
And that would be u equals negative x e to the, does that look right? Well, what does this become?
E to the x plus x. E
That's
to
just
the-
1 plus x now, isn't it?
Oh.
Yes? That's a little nicer.
Yeah.
Everybody cool with that? That's just 1 plus x when I multiply that x in there. I don't want to do 3 functions there. Oh my gosh, that'd be horrible. But x times 1 over x plus 1. Now, if I did this right, the whole left side, lest we forget, is d dx of mu times u. So it should be d dx of x e to the x u. Now let's check. Okay, first times derivative of second. Okay, right there. Second times derivative of first. Okay, derivative of first would be x e to the x plus e to the x times 1, which would be x plus 1 times e to the x, which is, oh, right here. So did I do it right?
Yes.
Yes. Whew. That's not really rejoicing celebration. That's more like, good, I didn't screw it up. That's the left side. I always do that. Without fail, I always do that check. What is the right side?
Negative.
Negative x e to the x.
It's actually.
I guess I'm going left still. Okay. Is everybody okay with that? I didn't lose anything, did I?
Well, it's actually pretty cool that you can check your answers a couple times during your differentiation process. Like once here, once when you get your answer, you can like.
Your very
differentiate.
final answer is the hardest one to check, because now you have to fit it into the original differential equation, which is not wrong, but to check it in this form is more work in general. Because what if y is kind of complicated? So
Well,
if I'm good here, then I know everything I have is perfectly correct. No, I have to integrate this guy still. Can I screw that up? Oh yeah. But how do I know? Well, I'm going to differentiate it to see I get this back again. That's my check. And if that happens, there's nothing left that I can mess up. I mean, we can try, but probably won't mess anything else up. So now I can say, and some of you keep forgetting that I'm going to integrate both sides. There, I just integrated the left. I don't need to write an integration symbol. I just integrated the left. But I haven't integrated the right yet. That negative in front can throw us if we're not careful, so I'd leave it in front. That's a simple integration by parts. What would my u be?
Negative.
X. Oh, I'm going to leave the negative. It doesn't matter. It's not going to change anything. And then the dv is e to the x dx. So the du is 1 dx, and the v is e to the x.
Yeah.
So this is the negative of,
UV.
did that just be? Or am I hearing things?
No, it's still good.
Yeah,
Okay.
negative x, e to the x.
We did lose the last, what, 10 minutes last day or 15
Yeah.
minutes something? And that battery pack is not,
It's
doesn't
dead
have a lot
now.
of dots.
So it's x times.
Okay, so x e to the x minus e to the x dx. So this is x e to the x minus e to the x.
Plus.
But I'm not worried about the plus c. I want to make sure I get that right.
Yeah, but minus.
So can I say then the right side is negative x e to the x
Plus.
plus e to the x? This is where I have to put the plus c in. My final answer is not going to have an arbitrary constant. It's going to have an arbitrary constant as a coefficient of another term. Because now I have to do what? I got to get rid of that. Ooh. So I'm going to be really lazy. I'm running out of room. I guess I'm going left again. It's kind of weird. I feel like I'm driving on the right-hand side of the steering wheel or something. I don't know. So tell me, what does u equal? It equals negative x e to the x plus e to the x plus c over x e to the x.
That looks like a bonus question.
Yeah, in a sense.
Yeah.
This is like problem number 6 or something. I don't know. This is an early problem in homework. Now, is that a correct final answer, or can I
You can
improve
sim-
upon that?
You can
You need to
simplify
switch
it.
back to.
Get rid of some.
Yeah.
Well, here's our dilemma. I don't want to do too much
Yeah.
because that's still a u. Oh, so yes, absolutely correct. I can split this up. That's correct. But do I want to split this up?
No.
I'm going to tell you why don't I want to split this up. Because what does this equal?
1 over y.
1 over y. Oh. So the reason I wrote it in this form is because I actually, right before I wrote it in this form, I looked over and said, what's our substitution again? Oh, it's a reciprocal of y. So I wrote it in this form. Yes, it's correct to split it up, but then when I do the reciprocal, I'm going to have to put them all back together again. So what does y equal? Equals x e to the x over negative x e to the x plus e to the x plus c. I can write something slightly better than this. If I multiply top and bottom by e to the negative x, that would probably be an easier answer, but is this correct?
Yes.
So what if I did this? Now what would be the point of doing this? I'd get rid of 3 of them, right? I circled this one. So this is the last step of the last step. If I do this, now my numerator is x and my denominator is negative x plus 1 plus c e to the negative x. Which, if I'm doing this on a calculator or a computer or anything, it's a little easier to deal with because I only have 1 e to the x as opposed to 3. Do I have to do that? No, but it's good to know that I can. Now, what if I gave you an initial condition And let's suppose hypothetically that the c ended up being 0.
Just get rid of it.
Where would I find that?
That's
I probably could find it the moment I did the 1 over y, because I would have a value for y. And I could manipulate it. Or you could wait until you get to here. Like we always said, it doesn't matter where you do it. But in a problem like this, because I've substituted the variable, you really have to wait till you substitute back. You can't do it for the u. That really won't be useful. So is that last answer a slight improvement? I think it is. Can I keep going? What if I did top and bottom by 1 over x? No, because then I'd have a 1 over x and I'd also have a quotient. So I know what some of you are thinking. I have a negative exponent. You can't have a negative exponent in your answer. I don't see any negative exponents. You? Where's the negative exponent? There isn't one. Wait, isn't negative x negative? No. Negative x is positive how often? Half the time. Negative x is neither positive nor negative. It's a variable. You can only not have negative exponents if they're numbers. So if our final answer was x to the negative 3, we'd say, no, that's 1 over x cubed. But if my final answer is e to the x is negative half time, is positive half time. Until I put a number in, it's neither. It's a function. So actually, that's absolutely correct. There is no advantage to putting 1 over e to the x. In fact, none of you ever wants to deal with 1 over e to the x. You'd much rather deal with e to the negative x, right? Decreasing.
E to the negative x versus e to the x just flips the orientation of it, right? 'Cause
If
it's all
graphically
one.
speaking, it would flip it along the y-axis. That's true.
Okay.
In terms of if I were to graph, if I were to enter this and graph this, if I were to enter this and graph this, it's the same graph. But if I'm doing, this is physics. I always like to use physics because in physics, you're not evaluating this at one value of x. You're evaluating at what, 30 values of x? Right? Maybe every 10th of a unit, right? As I'm moving down this, you're going to evaluate this a lot. I would do the second one because there's only 1 e to the x as opposed to 3. That's how I make the conclusion. The x's aren't going away, but I can have fewer e to the x's. Because we were flipping it over at the end. Now another hypothetical. Instead of 1 over y, what if this was y? Or I was even leaving it as u. I would definitely split this up. Why? Because then the first term would be negative 1. The second term would be 1 over x. And then the third term would be c over x e to the x. And that would be way easier to work with. But because it was 1 over y, I don't want to do that because then I'd have to take the reciprocal of that. Then I got to put everything back together again.
So if we're given initial conditions for y, could we plug that into our substitution and solve for an initial condition for u? And then that one
We could.
Okay.
Yeah, as long as it was something simple. What if? Because, let's suppose here's my initial condition. Y of 1 equals 2. Okay, something like that. Well, then what's u of 1? Because that's what you're asking.
Yeah, it would be 1/2.
Okay, 1/2. Piece of cake. You're absolutely correct. Everybody catch what his question was? Do I have to do it? Yeah. Now, so that was great. But what if that's not negative 1? That's negative 2. That's negative 3. That's a half. No, maybe not. Maybe that just makes it really ugly at this end and cleans up there. So because that was so clean and so nice, I would be very highly likely to do this. But I don't know that I would do that for all exponents. They can get kind of iffy.
So just to recap, to make sure that this is a Bernoulli, or that we can use the Bernoulli substitution, or
Yes.
If the f of x term in the linear ODE is a y term, then it is Bernoulli.
Well, no. The f of x, in this case, is actually 1. It's f of x times y to the n. In this case, my f of x is actually a 1. It originally started as an x, but when we got rid of the x, my f of x is a 1. Because if I get rid of that, that's 1 times. This is first order linear.
Okay.
This is Bernoulli. So when I rewrite it, I make a first order linear in u.
So it's Bernoulli because our f of x term is multiplied by a y term.
By a y to a power other than 1.
Okay.
Other than 1, really what it comes down to.
So we have 2 substitutions, and we have the polynomial substitution, and then we have the Bernoulli substitution.
You say polynomial, are you talking about the first thing we did today?
Yeah.
I don't know that I'd call that a polynomial because we said y equal ux. And the u-
It solves polynomial.
Well, it's to solve the homogeneous differential equation.
Homogeneous.
Yeah, I don't know that I would use the word polynomial in that context. That's a little too broad, I think. The two problems that we did today, I think, look substantially different. So you're less likely to confuse them. And what you always have to do is you have to practice. I think in this case here, sorry, where is it? There is a review section at the end of the chapter, and the author gives a lot of problems. That's the kind of stuff that's extremely valuable. I also have a practice test. I ask a lot less questions. But if I said, here's a whole bunch of problems from this particular section, you already know what technique to apply. Makes it easy. Then the next day we do it from a different section. Now, what if I just jumble them all together? That's where you know if you know your stuff. Because Calc 1, when you did integration, oh, that's going to be an inverse tan, that's going to be a natural log, that's a sine or cosine. Calc 2, oh, that's an integration by parts, that's a partial fractions decomposition. Once you could classify the problem, you knew exactly the strategy to use. But if I ask you this question and you're not seeing Bernoulli, now you're trying everything under the sun to no avail, right? You're just throwing stuff at a wall hoping it sticks. That's not going to work too well. I have to look at this and say, oh, it's a Bernoulli. And I can't do that without practicing a few Bernoullis. Knowing they're Bernoullis. Practice them. Practice your exact, knowing they're exact. So you can fly through. Then challenge yourself by going to a place like a chapter review where they're not necessarily in any particular order. My practice test.
Some flashcards. Some flashcards.
Sure. My practice test, which has been up since first day of class, now if you guys went and looked at it, you'd say, oh, I have a bunch of differential equations, and if I hadn't taken this course, they all look exactly the same to me. But now that I've taken it, I can clearly see this one goes here, this one goes here. That's the only way you can answer them. If you can't classify them, you're just going to stare at them. It's not a joke. You're like, I don't even know what to do to start it. And there's nothing more frustrating. And I have people come to my office all the time. They'll say, I don't even know where to start. And I'll say, well, what are we working with here? You know, what section is this from? I'll usually start with that because it might be a quiz question or homework. Well, what section are we in? That probably is a good, but sometimes I'll say, oh, I got this from the chapter review, which I say is awesome, but maybe we're not ready for that yet because we haven't done enough of each type. It is necessary at some point that you can do all of these seamlessly, right? You can't always go back and look things up, but that's just practice. But the best part is once you can distinguish them, and if you've just done a few, this question here to me is not absolutely obvious. This question here should be absolutely obvious. This looks first order linear except for this term. That's why I know it's a Bernoulli. But when I had it here and there's stuff everywhere, that's just thrown in there, right, to make it a little bit trickier. But the very fact that it's of the dy dx form as opposed to the differential notation. And if I'm looking in the textbook, the author in this section doesn't give you very many, by the way. Hold on. There are just a few Bernoullis. Hold on, like a few times. But all of the Bernoulli problems, he uses differential notation, dy dx notation, all of them. But the other ones, he mixes them up, the dx and the dy separately. And so you don't usually see that. Now, you had a bonus question on the quiz that is first order linear, but I used the differential notation. Why did you hate that? You should hate it.
Because
Makes
it's
it a
not
little harder to
obvious.
classify.
You didn't know if it was dy dt or dt dy. So you had to set it both ways and see which one gave me an integrating factor I could do. Which, by the way, technically you could do it both ways,
Yeah.
but I think one way was probably significantly easier than the other. But you could have actually set it up both ways. But because I didn't use this notation, it made it more challenging. Now, then how could you have even started it? Because of where it came from. I put it right there in the middle of those problems. That's the only reason you knew to use that technique, because that's what the whole quiz was. That question on an exam, probably not that question on an exam. Because you knew what it came from and it was still challenging.
Hey,
Now that you're gonna have 5 or 6 different, right? 5 or 6 different methods.
At first, I completely got it wrong because I tried to divide by the DTs and cancel some DTs out, and then I was like, well, that worked.
I like throwing bonus questions at you. By the way, never feel bad if you can't get a bonus question. It's just the opposite. Rejoice when you can get one because it means you're over and above the expectation. Now, having said that, many of you have been in my classes before, and I say things like this. To get a bonus question right at this level is awesome. Now you're at the next level. You're sitting in a class at UCSD, your junior year maybe. Guess who's sitting next to you? Everybody who could get the bonus question. In other words, what we consider over and above today becomes the generic at the next stop. Hate to tell you, this is why you have to do the bonus problems. You have to do them, because at the next stage, that becomes the general everybody can do, because that's who you're now sitting with. And that's scary. It's a scary thought to say, wait a minute, the stuff that's extra challenge now is the stuff I have to know at the next level? Yeah, because you're now in a higher class. It's not extra challenge anymore. But that's why it's important to challenge yourself at this level. Because if you only do the minimum to get by this level, then when you're at the next level, you're probably going to be at the bottom, because all the other folks did that stuff. That's why they're sitting there. Okay? It's not critical that you can do bonus net. But I think it's critical that you're always trying to challenge yourself, because every time you get one, then you can notch that up on your belt and say, okay, there's one more thing that I'm really good at that's better than I have to be. So who's sitting in this class? The elite at Mesa College. It's not a joke. But what class are you sitting in next year at this time? The elite who transferred from every other school. So those are now your peers. I knew a kid years ago. I taught high school many, many years ago. And we had a kid, he was valedictorian, brilliant kid. And he went to Harvard. And his first semester, and by the way, I didn't know this, at Harvard, the freshman classes, a lot of his classes, they graded on a curve, which I think is just pure evil. And by the way, none of you have ever had a class in your life, hopefully. You've never had a class that graded on the curve. And if your instructor said that, they have no idea what it means. That's a statistical term. It means you're graded based on your Z-score. Like you're based on everybody else's standing, which means if you're in the middle, you can't get anything other than a C. And to get an A means you had to separate yourself at least 1.5 standard deviations, which is almost impossible. I've never had a class in all the years I've been teaching where anybody was that far above. Why? Because the entire class is that far above. If I graded on a curve, there would be no A's, and there would only be a few B's. You'd mostly get C's because everybody's at the top. This kid got mostly C's, and he was ready to drop out of school. And we were talking about it. I said, so let me get this straight. You're in classes where they graded on a curve in most of your classes? He said, yeah. He goes, I've never gotten a C in my life. But by the way, these were in not core courses. These were in general ed mostly. So I said, who was sitting next to you? He goes, oh, every kid in the class was a valedictorian in his school. So I said, what you're telling me, you were average in a group of elite people. And you feel bad? He ended up graduating cum laude, by the way, from Harvard. But it completely flipped the way he was thinking. He's like, oh, have you ever seen the movie A Beautiful Mind?
Yes.
Russell Crowe plays John Nash, the super genius who he had that little small problem off to the side. You guys remember what it was? Yeah, it was schizophrenic. Yeah, his most important people in his life didn't actually exist, all that stuff. My favorite scene is that there's scene in the bar with him and all the other genius math people, and it's World War II, and they're working on code breaking and stuff. And one of his friends says to him, he goes, you're in a group of geniuses, and you have to be most genius? And he's like, yeah. And he was. He was